how do MSc people use machine learning within their work. I encourage you to take a look at these two articles. The first one, which is called Machine Learning and Materials Informatics, Recent Applications and Prospects, focuses on the applications. If you want more nuts and bolts material, like the mathematics behind machine learning, I recommend that you read the second article, Machine Learning Material Science, Recent Progress in Emerging Applications. Again, the titles are very similar, but I want to just highlight that the first paper is on, the emphasis is really on applications, or not much of the theory. But the second paper is sort of the opposite. Within material science, the term machine learning is sort of used loosely. Right? It could refer to real heavy-duty machine learning. It could also refer to data mining. It could refer to something called surrogate modeling. We'll talk about that shortly. It could refer to informatics type work. But really, there is overlap between all of these things, and these terms are used interchangeably. But here is the issue. Here is the scenario. If you have a material and you want to compute its properties, you want to predict its properties, we can use a DFT calculation to predict to determine its properties. Or the alternative approach is you can do experiments, right? You can procure the precursors, make the material, go to your lab, test it, and you can determine its properties. But both approaches, they have their pros and cons, but they are both laborious and expensive. DFT calculations are not cheap. They can take time. Likewise, experiments also require a lot of resources, and they can be laborious. But we do need to resort to one or the other, either experiments or computations, to generate data. But let's say you go through this process many times, and then you have a new case for which you need to make a prediction for its property. The question is, can you use the data that you have generated in the past and that data alone to make the prediction for the new case, right? And it turns out that it can be done, and that is where machine learning comes in. We go through this exercise called fingerprinting, and then the fingerprint is basically your X vector, and your Y vector is your property, and we establish a mapping between the X vector and the Y value. So let's say you use experiments or computations to go through this first arrow over and over again for a lot of cases, lot of material. So you've accumulated data. Now you use the data to train a model, and once you're done with all of that, you have a new material. You go through this path and make a prediction for its property. That's the idea in a nutshell. Right? And here is a little bit more detail. So your data set could look like that. You have material 1, 2, 3, 4, etc. through material M, for which you know the properties already. Either you have done DFT calculations to compute the properties, or you have done experiments to determine the properties, but you have this data set, let's say. It's an example data set. This is the starting point, right? And then here is the question. You have a new material X. What is its property value? Can you use the data set from this table and give the answer to this question? That's the learning problem. That's the formulation of the problem, right? Rather than doing a new calculation or a fresh experiment on material X, can you use the data, the table, and make an estimate, quick estimate? That's the idea. Turns out that under some circumstances you can, and it involves some steps. There are two key steps. The fingerprinting step, in which you can convert each of these material names to its fingerprints. Right? We're calling the fingerprints as the vector F. So you have several components in this fingerprint vector, and this vector F gets mapped to the property P. And that mapping process is what we call as learning, right? So there is the fingerprinting step, and then there is the learning step. If you can achieve this, if you can effectively do the fingerprinting and then also the learning part, you will have a function F which is a fingerprint component, and it will give you the property value. Once you have this function, you can now answer this question. Material X is the one whose property you want to predict. You convert the material X to its fingerprints, F1, F2, S3, etc. Stick that into your function and get your property value. That's your property value for material X. So that's the basic idea of machine learning in material science. And as I said, it has several steps to it. The first step is you need data. If there is a problem for which there is just no data, machine learning is not your tool. Okay, either you have to have a fair amount of prior data, or you need to put some effort to create data. So that's the first step: data curation, data collection, and data curation. That's the first step. The second step is fingerprinting. You convert each of those cases into vectors, right? And then the next step is machine learning or surrogate modeling. A surrogate is a nice word for substitute, right? You're really substituting the actual experimental procedure or the computational procedure, TFT procedure, with a surrogate, which is the machine learning model. So machine learning modeling is also referred to as surrogate modeling. Statisticians came up with this a long time before the term machine learning was coined. But philosophically, it's the same thing. Once you have a model established, then you have a property prediction scheme, right? So which you can now use to make predictions for new cases instantaneously. And if you succeed in all of this, you have a knowledge system. So this is the pipeline. This is the workflow we generally adopt within material science when we use machine learning methods to develop these predictive models. Okay, all right, let's move on. First, data curation. One good source of data is calculations that you can do, right? So let's say you want to study the density of various metals. Okay, so maybe you can do DFT calculations to find out the equilibrium lattice parameters, and from that you can calculate the density, right? For a variety of materials. So you could do that. In other words, what I'm trying to say is you can create data using computations, or you can do experiments and create your own data, or you can get data from your collaborator's lab, from your coworker or collaborator's lab. You can obtain data, right? You create it yourself, or you get it from your colleagues, or you can get data from the literature, right? You can laboriously extract data from the literature, which is what I call as manual or human mining of literature data. Or you can use one of these fancy, nice new methods that are coming along. Example, natural language processing. And we are doing that in my group. We're building the capability to use NLP, or natural language processing, to automatically and continuously extract data from the literature. That's another source. Can somebody think of other sources? Yes, historic data sitting in lab notebooks. And this can include good, successful experiments as well as failed experiments. You see, a lot of times when you try something and it does not work, we don't publish them, do we? Because only the cool stuff they find their way into journals, because that's what we think are publication worthy. But you see, failed experiments are equally important, and they can be found in our lab notebooks. We never publish them, but they are there. From a machine learning point of view, successful cases as well as failed cases are equally important. And here is another massive source of data, right? Materials repositories. There are a lot of great repositories already out there. There are many that are mushrooming right now, especially because of the data revolution we're going through. You see, here are some examples, MatMatch, MatWeb, zeolite database, if you're interested in zeolites, polymer database, CRC handbooks, right? Okay, let me go back to my laser pointer. CRC handbooks, you see, that's another great source. Elsevier has this app that you can use to extract data. National Institute of Material Sciences is a Japanese initiative. ICSD, International Crystal Structure Database. Matin, this is a Georgia Tech production run by the iMat. And then there are these things, other things I show down below. These are purely computational. The stuff that you see above, they are mostly experimental data. The stuff that you see down below, Nomad, Aflow, etc., these are computational databases, meaning the DFT calculations have been done by many people, and they have been archived in these different places. Kazana, the last one, is a platform that we are maintaining in my group. Whenever we publish a DFT article, the data from the DFT paper is contained, can be accessed, open access at kazana.gatech.edu. So data can be obtained from any sources. That's the point I'm trying to make, right? So little bit more. Let me give some specific examples of how a data set could look like. Here is one. Let's say your goal is to develop a predictive model of the band gap of complex oxides. I believe everybody knows what a complex oxide is, right? What is a complex oxide? Okay, so a simple oxide is just a metal and a compound that contains a metal and an oxygen and oxygen. Okay, so it's just the oxidation product of a simple elemental metal. A complex oxide involves two different elements, and of course oxygen. Right, so that's a complex oxide. So barium titanate is an example. Calcium arsenate, lead titanate, etc. Okay, these are all complex oxides. Okay, so let's say your goal is to develop a model, predictive model that can instantaneously predict the band gap of complex oxides. What would you do? You would go look in the literature to see, to determine, to find out if people have studied the band gaps of electronic structure of complex oxides, and you collect that data. And your data set could look like this. You'll have a listing of various complex oxides and the corresponding band gap values. Here is another example, going to the polymer domain, right? Maybe your goal is to develop a predictive model of some particular, right? The glass transition temperature in this case, right? So again, you will have a listing of polymers and the corresponding TG values, assuming this is available in the literature, right? You go to the literature, go to the handbooks, go to repositories, and you collect all this data and you assemble a table. And the data set does not always have to be material versus property, right? It could be synthesis conditions versus outcome. For example, you're in a group that does synthesis of materials. You're not measuring properties, but you're making stuff. So maybe you use some conditions, processing or synthesis conditions, temperature something, pressure something, and then you got a good sample. And then there are other conditions that give you bad samples, poor quality samples. So you have a variety of process conditions and a listing of those process conditions and whether you got a good or a bad sample, right? So that's another example. Or maybe you are doing catalysis work and you have a variety of catalysts that you have made and you have tested. And some catalysts have high selectivity for the reaction you're trying to study, and some have low selectivity, right? And maybe some have medium selectivity. So it doesn't have to be binary, right? It does not have to be just high or low. It can be various gradations. The point I'm trying to make is that here is how your data would look like, right? This is the starting point. You would collect information of this type, right? Okay, all right, let's move on. Fingerprinting. So let's say you collected your data, right? You have the data set of interest. For example, if your goal is to create a predictive model that can instantaneously predict the melting temperature of inorganic materials, oxides, let us say, or metals. So what you would do is you'll go look up handbooks, repositories, etc., and collect a variety of metals and alloys and their corresponding melting points. That's what you would do upfront. So, but now remember, you need to represent each of these cases in terms of a string of numbers, which is what we call as fingerprints or descriptors or features, etc. Right? How do we go about doing that? So we have collected the data, material 1 through material n, and the corresponding property values. The next step is fingerprinting that one. We have to convert each of the materials to a set of vectors. Okay, here is the data that the example data sets that we discussed just a little while ago, right? Materials versus band gap, polymers versus TG, synthesis conditions versus outcome, material performance data, etc. Right? Now, here is the goal. Here is what we need to do. We need to convert each of those items that I've circled in red into a string of numbers. That's our X vector, right? How do we represent these things numerically? How do we represent polyethylene, polystyrene, polycarbonate, etc., 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 numerically? How do we represent them as vectors? In other words, how do we barcode them? Essentially, we're trying to numerically barcode each of them, right? Catalyst A, catalyst B, catalyst C, etc. How do we convert them to vectors? Catalyst A could be platinum nanoparticles of a certain size on a silica substrate. Okay. Catalyst B could be rhodium nanoparticles of a different size on alumina substrate, etc., etc. How are we going to convert them to numbers? That's the question. Okay. Because we need them to be numbers because we want to map the X vector to the Y vector, right? Using some algorithm. That's the ultimate goal. Okay. So here are some rules that we generally adopt. There is no magic bullet. There is no silver bullet. There is no easy answer to a question of how do we go about fingerprinting. There are some ideas. Numerical fingerprinting is the numerical representation of a material, process, or case, also referred to as feature vector or set of descriptors. Here's the thing, they should be easy to compute. The fingerprints should be easy to compute or easily available. They should not be very complicated to compute. Then it totally defeats the purpose of doing it instantaneously, right? They should be easily accessible, easy to compute stuff. They can vary in length scale. Those fingerprint components, they can be defined at the atomic level. They can be defined at the subatomic electronic level. They can be defined at the, mesoscale level, macro scale level. They can be at different length scales. And I'm going to give you 3 examples, okay, shortly. And this will answer the question that was asked earlier. They should also be invariant to certain transformations. Let's say your goal is to compute the energy of molecules, let us say, right? Total energy of a bunch of molecules. Of course, if you rotate the molecule or you translate the molecule, the energy does not change. And so your fingerprint vector should be invariant to such transformation. So, but we don't have to get too much into that. And of course, the fingerprint vector should not contain irrelevant components, right? And here is the thing. This is perhaps the most important part of the entire pipeline. It is not the machine learning algorithm itself that is as important as this step is. Of course, without data, you can't do anything. You need data. That is the 0th level, that is the 0th order requirement, right? Without that, you can't do any of this. But assuming you have data, the most critical step is actually this fingerprinting step, right? And you need a lot of experience and intuition and knowledge about problems of this nature to be able to properly do the fingerprinting. So I'm going to give you a few examples of fingerprinting, okay? One class of fingerprinting can be very high level features. Let's say your goal is to figure out, is to predict some complex property like when a material is going to fracture, when a material is going to fail, okay, or when a material is going to under electrical stress, under mechanical stress, when is it going to fail? That's what we call as fracture, right? Under electrical stress, when is the material going to fail? That's another scenario. So let's say the goal is some complex property that depends on so many intrinsic factors and extrinsic factors, right? So in such cases, you may actually choose certain high-level features that are easily accessible or easily computable, such as this. Your descriptors or fingerprint components can be these things that you are seeing: band gap, dielectric constant, density, bulk modulus, and so forth. And your target property could be something like fracture strength, fracture toughness. Okay. Now, do we use just these properties just as they are? You could. That is one approach. there's another approach, which is you kind of perform some operations on these features. Um, so in this example that I'm showing, so you have eight, right? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 features, right? Eight primary features, 8 primary features. You can actually consider a bunch of prototypical functions, right? The features, X basically means the feature themselves, the reciprocal of the feature, square root of the feature, etc. And then you can actually combine those features subjected to those functions. For example, why do you get 96 here? 12 times 8 is 96. You take each of those features and take the feature itself, the reciprocal of the feature, square root of the feature, etc. You'll have 12 from each one, and there are 8 of those, so that's 96. Then you can multiply, cross multiply, right? You can take the band gap as it is and multiply it by the reciprocal of the dielectric constant. And so by cross multiplying, you can get a lot. And then by considering three products involving 3 things, you can get a lot more. So like this, you can actually generate compound features. But by now, you have a lot of features. You have 200,000 features. So now you can do down selection. You can throw away things that are not required, keep only the things that are non-redundant and irrelevant. And there are ways to do that. We're not going to get into that. I'm just saying how one would go about crafting features, right? So this is one example. I'm going to show 2 other examples, and then I'll ask you guys for questions. I'll ask you if you have any questions. Here is a second type of fingerprinting, right? Let's say you're interested in polymers. We all know that polymers have a lot of monomer units, a lot of fragments of this type that you see, right? This could be a fragment that you could find in a polymer. This is yet another type of fragment. So let us say you assemble a catalog of possible fragments that you can find in polymers, right? It's a countably finite set of fragments that you can come up with that can occur in polymers, and then you simply count how many of each fragment you find in a polymer, and that's your fingerprint. The fingerprint of polymer high is it's a vector, and for example, this thing here is a number fraction of the fragment type 2. So maybe that's type 2. So you find out how many times this particular fragment occurs in that polymer I. Then you put that there. So that's your fingerprint component. Likewise, you populate this vector. This is another way of converting a polymer to a vector. For example, polyethylene is a sequence of CH2 units, right? So let's say the first one here represents the CH2 fragment, and the others are other fragments. So for polyethylene, it will be just 1 followed by all zeros, and so forth. So here is another strategy, right, to fingerprint materials. And you could apply this for inorganic materials as well. Here is yet another way. Here is going down to the atomic level, right? This is particularly useful for DFT people. So you say, okay, I have this the 3-dimensional lattice of at on various points. We have atoms of different types sitting, and so I'm going to go to a particular atom, let's say atom I, particular atom, and I'm going to keep track of what other atoms are around it and how far away they are. So that's why you see all these different concentric circles, right? Within this red circle, there is nothing. Within this orange circle, oh yeah, there are a few. And then within this green circle, maybe there are more, and so forth. So that way you can fingerprint the environment around atom I. Okay. So this kind of fingerprinting strategy is very useful when you want to capture microscopic or nanoscopic information. So now let's go back, right? There is a gradation. These are all higher level macroscopic level properties that you have. You are fingerprinting materials in terms of higher level features. Here you are fingerprinting materials in terms of not at the atomic level, but atomic connectivity, fragments, molecular fragment level. And here it is, the resolution is high, right? You're going down to the atomic level and fragmenting. So there are different ways, and there are a lot of other hybrid ways as well, right? You can combine different levels, different scales as well. So those are examples of how would one go about fingerprint. All right, okay. So let me move on, right? So what have we accomplished so far? We have collected a data set, let's say, and then we have fingerprinted. So we've done the fingerprinting, and then finally we need to do the learning, right? So now we need to map these fingerprint vectors to properties. We need to do that mapping. And strictly speaking, that is what we call as the learning process. We are learning the relationship between your fingerprint vector, between X or F in this case, and P or Y, right? XY mapping. The most elementary way of doing this mapping is something called linear regression, right? So it's nothing but making the hypothesis that P, right? P is a linear combination of the F's, right? P1 equals some C1 coefficient C1 F1 plus times F1, 2, etc., etc. Where C1, C2, C3 are coefficients. So you use this data set, right? You use this entire data set and find out what the coefficient C's should be. Right? So it's a very straightforward, trivial process. You can even use Excel to do it. And it's a very powerful tool, by the way. If you kind of use, let's go back. Huh? Let's say you use this procedure, right, to create 200,000 features. It's a lot of features, right? So you can actually do some down selection, and then after that you can use the linear regression, for instance, to establish a mapping between the remaining features and P. And it works quite well, and we have done that in the past. And I'm going to show a paper at the very end of today's lecture where we explain how that can be done quite effectively. It's a very simple thing, right? Linear regression is the most basic thing we can imagine. And in some circumstances, it's quite powerful. But in most circumstances, it is not very effective. Okay? That is why we need to go after more sophisticated algorithms. Linear regression is one of them, right? Surrogate modeling for machine learning or surrogate modeling. And then there is this thing called lasso. I unfortunately don't have time to go into it. It's a very beautiful method. It's a very clever acronym. Lasso stands for least absolute shrinkage and selection operator. What it does is, remember when, sorry to switch back and forth. Remember this slide. So you can start with 8 primary features, and then you can do all this, use these prototypical functions, and at the end of the day, you can craft 200,000 features, let us say. But that's too many features. Out of the 200,000, you want only 5 that are most relevant to the problem you're trying to study, let us say, right? You can use this thing called lasso. It's a clever acronym because it gives you the visual impression of you are lassoing those 5 features out of the 200,000 features that are most relevant for your problem. It allows you to lasso the 5 or small number of features that are important, right? You do the lasso first, and then you can do linear regression on those few selected features, right? It's really cool. There's something called K nearest neighbors. It sounds cryptic, but it's very simple. What you do is, you see, the learning problem is you have a new case and you want to find its value, right? Find its target Y value or property value. What you do is you take the fingerprint of that new case, unknown case, and then you compare its fingerprint to the fingerprint of all the known cases you have seen before from your data set. Just like Netflix compares your fingerprint to the fingerprint of a movie, you can use a dot product comparison. And you find the K closest fingerprint from your data set. And you find the average value of those K cases. And you say that is the value, most expected value for this new case. So it's called K nearest neighbors because the K, you take into consideration the K candidates from your data set that come closest to your new case. And you find the average and then say, that's it. And then there is something a little bit more sophisticated, kernel ridge regression, or its close cousin, Gaussian process regression, KRR or GPR. Very beautiful methods. Up until recently, they used to be my favorite. They still are. This is actually a little bit more sophisticated than the K nearest neighbor approach. Instead of just choosing K, k nearest neighbors, why don't we just do a weighted average? The closest neighbors should get more weight, right? The ones that are farthest should get less weight. So you do a weighted sum of all the members of your data set, right? And then make a prediction. That's sort of, in very simple language, that's sort of how KRR or GPR work. So you see, the first one is linear regression, and these things are highly nonlinear. Okay. And then there are these things called random forests and decision trees. You may have heard of them. Very cool. They have their pros and cons. Each method has their pros and cons. And of course, there are neural networks. Right? So in the next couple of slides, I'm obviously not going to have time to cover all of this. In the next two slides, I'm just going to give you a flavor for how this KRR or GPR works, and then also a flavor for how neural networks work, right? And of course, there are many more. And these days, there's just an alphabet, so there are like compendiums written on the different algorithms that one can use. There's just way too many out there. And the beauty is that there are also these lot of packages that are available, modules available, in the Python or the R programming languages, which you can actually use to do a lot of these things quite effortlessly. Let's talk about kernel ridge regression or Gaussian process regression, right? So look at the picture on the left. Just a reminder of our, it's a small part of our data set, right? So we have fingerprinted them and we have the properties. And our goal is to map the fingerprints to the properties. Find the functional dependence. Find a function that connects F to P. That's the goal, right? So you have 1 through n cases for which you know the P value. And you see these red spots, 1, 2, 3, 4, etc. red spots. Those are the cases for which you know the P values. And those are the cases that are shown here in this fingerprint space. This is the fingerprint space, the multi-dimensional, high-dimensional space. These are the points in that high-dimensional fingerprint space. And this is a new case I, which is in green, right? And that is the case for which you want to make a prediction. You know the answers for 1, 2, 3, 4, and you want to make a prediction for I. So what do? You find the distance between I and 1, I and 2, etc. So these are the distances. Okay. And then the property value of I, sorry, yeah, there's a typo here. Should be I. Property value of I is really a weighted sum over all of these other cases and weighted based on the distances. The distances are here. Okay. That's sort of how your kernel ridge regression or Gaussian process regression works. And these are extremely powerful methods. If your data set size is smallish meaning not more than a few thousands, these are the methods of choice. Okay. They work remarkably well and very efficient. But if your data set size is much bigger than a few thousand, 10,000, 100,000, million, billion, you don't want to use this method. It scales very poorly. Then you would choose something like this, neural networks, which many of you would have heard of, right? Again, the problem is the same thing. You're trying to map this vector to that value. And you have a lot of examples. You know the answers. So you train a neural network. This is your neural network. See, these are the inputs. Input 1 through 4, 1 through n, for example. You have, these are called nodes. Input is called the input layer. And you have a bunch of nodes in the input layer. And then there is the output layer, which in this example is just one value that you are going to predict. And so you have one node, which will spit out a number. The input nodes, each one will take a number. And what are they? They are the fingerprint components, right? So for example, input 1 could be F11, input 2 could be F12, input 3 is F13, etc. So this vector gets fed in here. That's why you have multiple nodes. And then this property value P gets spit out. And then you have hidden, in this example, I'm showing one hidden layer with a bunch of nodes, but you could have many hidden layers with many nodes, right? And what does it really mean? It sort of look mysterious. This is really inspired by how our brains work, right? Each node here can be viewed as a neuron. And we all know that you have a bunch of neurons, and then neurons are connected to each other through this thing called synapses, right? And each neuron fires, and if the firing of a bunch of neurons that are connected to another neuron, if the collective firing crosses a certain threshold, then that neuron fires, and then it cascades through. This is exactly how this architecture constructed, right? So this could be one example, one possible hidden layer neuron node, and you have a lot of inputs from this previous layer, right? And then there is a function that determines whether you've crossed the threshold or not. If you cross the threshold, it gives some value to the next one. It keeps propagating like that. And this is nothing but an architecture that performs a highly non-linear mapping between this and that. There's a hell of a lot of literature on how these things work, right? But that's all I will say at this point. Right? Questions? Any questions so far?
Can I ask a question, Professor?
Mm-hmm.
It sounds like neural networks are the most popular in practical application. Is there a reason why?
Actually, that is not entirely true. As I said earlier, it depends on your data set size. Uh, what is happening today is the people who are doing machine learning, who are popularizing machine learning, are people who really fall in the big data domain, meaning they have a lot of data. People in searches, example Google searches, people in e-commerce such as Amazon, in the recommendation area, Netflix, or gaming or weather prediction. There is a lot of data. When you have a lot of data points, right? When you go back here, when you have when I say data point, I mean this is one data point, right? That's one data point. This is a second data point. This is in this example, there are n data points. If n is of the order of millions or billions, really your neural networks are perhaps the one. There are some other options, but these are the best options that we have today. In order to handle such a massive amount of data, you got to use neural networks. So it depends on who you talk to. It depends on who you are talking about also, right? People who deal with enormous data sets, they will generally tend to use neural networks. On the other extreme, there are people who deal with small data sets, and material scientists are examples of that. Okay, material scientists, mechanical engineers, and in traditional the hard sciences and engineering, your data set sizes are not that big. Sometimes you have just 100 data points. Okay, sometimes you have 1,000 data points. But when you fall in that domain, you do not want to use neural networks because they do this thing called overfitting. Okay. And so you really you better be very careful if you're going to be using a neural network when you have only 100 data points. You are much better off using this algorithm. This will work really very well. So when you are in the small data situation, you use something like this. If you are in the large data situation, you use something like this. So okay, that's the answer I have for your question. Okay, all right, let's move on. So this is just a summary slide, right? This is the starting point. You got to have this to consider machine learning as an option for you. And then, of course, this is the question. This is the sort of question you're trying to answer. If you have n cases for which you know the answers, here is case X. What is the answer to that case? You go through a fingerprinting exercise. You convert all these textual labels, material 1 through material n, to fingerprint numbers. And then that's a fingerprinting step. And then you do the learning step. And after that, you have a function that maps your fingerprints to your property. And then you have a pathway to predict the property of the new material X. Right? So here is also a repeat slide. You see, within material science, we are very good at this. We can make a sample, make a material and test it, do physical characterization, electrical characterization, etc. And we can generate data, or we can do calculations. You can use density functional theory or some other computational method. and we can produce data. But the revolution that we are talking about right now piggybacks on these traditional approaches. We cannot replace the traditional approaches, right? We leverage off of the traditional approaches. Machine learning is not intended to replace everything else. It is expected to partner with these other traditional approaches. That's my outlook, right? People are very scared. They say, "Oh, machine learning is going to take over. AI is going to replace everything." Actually, I don't know about that. It's. I would like to look upon this as a partnership between the human and the machine, right? So we have this other pathway. Provided this thing produces a lot of good information, good data, we can go through this pathway to accelerate, to augment the traditional approaches, right? So I do want to, okay, this looks busy. I do want to show a few things in case you guys are interested in learning more, right? So there are, of course, these two papers that you can look at. But if you want to know about some specific examples, sometimes that may be more helpful, right? What I would say is read this second paper, which is the short review paper. Read that paper, and then you can go on to one of these specific applications, right? So let me talk about this. So just a reading for material scientists interested in machine learning. So let's talk about this thing here, right? The top one first. This came out 3 or 4 years ago from my group, and so here it's a small data problem that we solved, right? We solved this problem of we wanted to answer this question of when will a material break down when subjected to electric fields, right? What is the critical electric field above which an insulator becomes a metal? It basically breaks down, right? So we wanted to answer that question, and we created our own data set, and then we used that lasso. Remember I mentioned the lasso method? We created a lot of features, then used lasso to compact the feature set, came up with a few features, and then used linear regression, right, to establish a beautiful relationship between the dielectric breakdown strength of the material and other simple properties. So that's one of the early articles. I recommend you take a look at that if you're interested in that sort of stuff. This thing here, polymer genome, is a ongoing active development in my group, where our goal is to be able to predict the properties, a variety of properties of polymers. So there is a website, polymergenome.org. You can actually go there and even draw your polymer and then hit the predict button, and then it predicts a variety of properties for that polymer. And how it works actually is explained in this paper, right? So that's a picture of your polymer, representation of your polymer. And then we take that as a starting point. It goes through a hierarchical fingerprinting. Fingerprinting is done at different length scales, and then models are developed and which make the predictions. And here is another article, a very recent article, just came out last year, where we explain how one may go about fingerprinting at the very lowest, at the shortest length scale, right? High resolution fingerprints for materials and atoms and molecules, right? So this paper actually explains the fingerprinting procedure that one can adopt. And this paper over here also came out very recently last year. It uses this fingerprint, the fine high resolution fingerprint scheme, and it actually shows how one can learn from DFT calculations and emulate DFT 8 orders of magnitude faster. Basically, it's a quantum machine. It's a machine that learns quantum mechanics, that learns elements of density functional theory, and then for a new case, it can perform what a regular DFT code can do, but much, much faster. It's very much in progress, but it's a very exciting frontier. So with that, I'm going to stop. That's really all I have.